Morning, everybody. This is Mankind in Training, and I am your host, Joshua Parr. Today I have some Python examples showing how versatile the Python programming language is. I have some calculus, linear algebra, and like some graphing examples, how to change things in your figures and visualizations. So I'm going to share my screen now. Python is an incredibly versatile language. It really is. And I'm going through and showing how to use some of the NumPy functions and how to do some plots with Matplotlib. I recently got a request to do a deep dive in C++, go back to the beginning and go on forward. And I do plan on doing that. That is one of the videos coming up soon. But for now, let's get into this one. This is Python. I'm currently in a Jupyter notebook that you can get through Anaconda. And in this first cell, I am creating a series of variables, A1 through A7, and showing some of the various NumPy functions on how to create arrays. First, you have to import NumPy as NP and import matplotlib.pyplot as PLT. In this very first one, I'm creating a NumPy array with just 4 elements. In the next one, I'm creating a NumPy array of nothing but zeros, and it's 30 elements long. Doing the same thing with ones. It's an array, 30 elements long, entirely ones. A4 np.random, I will be getting a bunch of random integers. And then in this one, I believe it will give you a bunch of random floats or longs. And then linear space. It is starting from 0, going to 300 by 30s. And A7 is np.arrange, and it will arrange from 0 to 30 every 0.7. So this first operation, I'm taking A1, which was just this array, and I'm multiplying all the elements of that array by 3. You can also change it to whatever you want. It will give you the values. So in this next one, I am asking 3 times the elements in A1 to return all of them that are less than 30 or greater than 30. And none of them were, so it returned false for every one because oh yeah, the original was definitely under 30. And here 3 times A5 plus A4 gives us a new array again. This is a plot. This is how you would plot with Matplotlib, and I'm plotting A6 here, and the line from the point A6 to the point A6 squared. So this is a exponential increase. I'm now doing a histogram of A7. That was this one. I'm now doing a histogram of A5. Simple how you do plots and histograms. They're not too difficult. Now I'm creating a function, f of x. And any number I put into this function, it will return that number cubed times sine of x. That's another NumPy function, divided by all the exponent elements of negative x. So this plot will be plotting A6 here. And when you run A6 through this function, f of A6, it ends up there, and it's plotting the line all the way there. A2, I'm creating another element now, and it will be a bunch of random numbers 2 times random integers, 15,000 of them. And then now I want to find the mean of the array I just created, and it is 29. Now if I want to find the standard deviation, that's this function here of the same array, we get 2.011 and a whole bunch of other numbers. If you want to get the percentile of 82, the 75th percentile, it's 31. So now I'm creating, we're getting a little bit into our calculus here. I'm creating an x-array linear space function. And now I'm creating y as being 2 divided by x squared times sine of x. And then dy dx being equivalent to the gradient of y and x. Then I'm creating a y integral. I'm getting the integral by the cumulative sum of y and multiplying it by x1 minus x0. And then I'm plotting this, and plotting this, and plotting this. Now, when you do them all three together in the same cell like that, it's going to plot all of them over each other. So this is what that looks like. Now I did another simple one here. I'm creating an array, another linear space array, and I'm finding negative x divided by 33, the exponent elements, times cosine of x. And then I'm plotting x versus y, and you get this. Now, if you want like the opposite of that, sort of, you would put sine here, and you get the other position here. So this is against sine of x, and this is against cosine of x. Now, if you want to create bounds and find things within the bounds, I'm asking for the mean of y of any x being greater than 4 times any x being less than 7. And then doing the same thing again, find the standard deviation, and that will output that. So now I'm trying to ask for the percentile with a similar set of bounds, the 75th. Queues it up for you nice and quickly. Now I'm trying to find the mean and standard deviation again with different bounds. I use 7 here. I'm using 9 now. You get a different number. So now I'm plotting negative x against the gradient of y and negative x, and I get this nice little lib plot here. I'm now dy dx, I'm creating a new element, and it's being equivalent to the gradient of y versus x. And then this is how you return bits and pieces of the array. You can be specific. This one is asking for a specificity, and it's returning it. np.arrange. This is mod 12, mod 3, and then sum them all together, and this is the number I get. These np arrange functions are, we've seen this up at the top already. It will arrange them how you are saying 0 to 1001 by 1, and then return only the things divisible by 12, return only the things divisible by 3. So in this one, this was shout out to P Solver, by the way. A lot of these examples I learned from him on how to do them in Python, because I know how to do some programming in Python, but I wasn't entirely sure how to do calculus in Python. So Mr. P Solver on YouTube really helped a lot with that. Some of these functions, like this one right here, were taken directly from his GitHub page. I typed them right over exactly how he had it. That is this right here. He made a flower using calculus. Now, what I did was I flipped it on its head. I took the information he gave me and returned the exact opposite of it and changed the parameters a little bit. Flower, flower. That one's inverse from the other. I am creating a new variable a being half the sum of r squared times theta 1 minus theta 2. And that's finding some bounds here in this flower. It's finding the area probably in the flower. And then L is finding the length of the line, the perimeter of it. That's what it looks like these functions are. This is creating a plot similar to the one we had initially. It looks very similar to the very first plot I showed you how to do, except for now I am adding labels. And for mathematical functions, we have the dollar sign here. That is symbolizing that it wants you to do the math style over here, and then a KT on the bottom. It's K over A sigma epsilon of T, and its time is going to 4. There's 4 indices, 0, 1, 2, 3. And against E of KT on the other side. So A1, creating a new A1. We started with A1, I'm changing it now. It will be an NP array, a 3x3 NP array, and I am showing all of the elements in it. I am declaring all the elements in it. It's not creating any random ones. Bam. That is how you would do a 3x3 multi-dimensional NP array. So now I am dividing, 3 divided by A1. I'm returning that. Now, I made a 3x3. If you want to take that 3x3 and turn it into just a single dimensional array, you use the ravel function, a1.ravel. And it raveled A1. It'll get rid of all of these square brackets and put it all into a single array, just like that. Asking to return all of A1 greater than 5. The first element was 100, true, greater than 5, greater than 5. And then 102 is also greater than 5. But 2, 1, and -1 are all false. And then 5 is false because it's not greater than 5, it is 5. 6 returns true, it is greater than 5. And 11 returns true, 5. Now I'm creating another array of randoms. Now when you use rand n, instead of just like a normal integer, you're going to get a float of any various size, and it's usually going to put you in the E range. This array created that. So now it looks like I'm getting long on time already, so I'm going to try to do these quickly. A1 is this again. Now if you want to return the 0th row, so there were 3 rows. The 0th row is the first row, 100, 101, 102. It will only return that. Now, if you want to return the last row, which would be the second indices, A1 of 2 will return that indeed. Now, if you want to return the first column, if you want to return the second column, because this would be the 0th column. So the second column is 101, 1, and 6. It indeed returns that. If you want to negate the very first one in the top of that row, you would write it like this and only return the 1 and the 6. Now, you can take and resize an array and name it a different thing, like I'm creating B1 and using A1's resize, I'm doubling because A1 was a 3x3 and now it's a 6x6. So basically what it did was just take it and double it. And now it's a 6x6 array. Takes all the values and then repositions them again. And then all these are how to return specific portions of your array. I'm using my hand and I shouldn't be using the mouse. B1 now will return U1, 2, and 3. A1 again, just to show. Now, this is how you create a color bar, a contour. I'm using X and Y and X and Y, creating linear spaces and then meshing the grids because they are two different sizes. If you try to do this without the mesh grid, it will return an error. So this is cool. I did this same thing in R. This is the technique for doing it with Python. If you have a linear system of equations to solve, you can use this function, linear algebra solve. So here's my coefficients. No. Yeah. So like if I have x, say these are x, y, and z, it'd be 3x, 2y, and z. 5x, negative 5y, 4z. And then equals 4, equals 3, equals 0. So it's like the same exact technique as I used in R almost. But now we're in Python, and NumPy has a function called linear algebra.solve. A and C being the answer. You want to do them in that order too, or else it's not going to work how you want it to. These are the coefficients. This is x, this is y, and this is z. To fit all of those bounds, it will work for all of the equations listed. Now I'm creating some arrays and just doing some operations on them. If you want to find the dot product of B1 and B2, it'll find it for you. If you want to find the cross product for B1 and B2, it'll find it for you. Here's another linear algebra solving to find the eigenvalues of A and return them. Now, I'm doing something similar here to return V of A. Now, here's another example of the color bar. Here is summing the absolute value of when you ravel. I'm returning some values. Here, I am creating a Z line and a T line, and then measuring them over time, T of B, and then plotting them over each other. Now, here's one where I'm taking the blue line, swapping the axes, and plotting them over each other. Here's just the swap of the blue. Now here is a good example of some calculus. Taking derivatives, finding eigenvalues, creating matrix, and plotting them. Here are just some, so you can take and multiply pi, or we're squaring pi here, and then w of -1 returns almost an identical value. to the 100th position, and around the 1000th, they diverge. Same thing here. If you do 2 times np.pi squared, you get the same thing as returning w all the way to the 100th position, and then it diverges at the 1000th. Now we're getting into just some matplotlib, how to plot things. So I'm taking an x and a y and plotting them. One being a linear space and the other one being sine of x times 0.1 times np.random.randn, the length of x, 36. Or no, 12. Yeah. And then I'm taking the same plot and I changed it. So, and if you put like a dot and a dash, it'll have one less dash in between the dots. Or if you do straight circles like O, just do O, it'll be nothing but dots. You can change the color to here. Let's do that. You can do pretty much whatever you want. Let's go red. Let's make the line skinnier. Let's do that. You can take and fiddle with these, and I recommend that you do. It's the best way to learn how to do things. If you see something that you liked here and you think it might solve a problem that you're working on, go ahead and pause this video and you're welcome to take this code. I will download. I will try to find a link to this notebook. Maybe I'll add it into the video. Or psolver has pretty much these examples too. They're just a little bit different. Now this is taking that same plot and making it longer, so you can see a little bit more of what's going on. Making it longer, making it skinnier. Now I'm same plot. I'm just adding things on the y-axis and the x-axis, and then this is a title. As you can see, plt.title, voltage in the third electrode, da, 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 da. You can put whatever you want in here. Josh is cool. Yeah. And it will totally say Josh is cool. You can put whatever you want in here, and that's how these work. It's very simple. Now I'm adding same plot again. I made it a little bit smaller and added this here, component 1. Did it again now, except for I changed it. So now we have the data and the fit line. And same thing, you can change any of these labels to say whatever you want. You can change the color of the line, all of it. So when I did this though, you see data and fit are like in the line. I didn't like that. So you can change the position of it like I did here and have it in the top corner, and then it's not in the way of anything. So now I'm creating a variable called res, and it's just a series of randoms, 1000 times 0.3 plus 0.6, and then I'm making a histogram of res. Now, same histogram, same values, more bins. I've added bins, and it's a little bit more accurate, and it's going to get more accurate the more bins you add. So add 30 bins, you get to see a little bit more of what's going on. You add 50 bins, you see a little bit more of what's going on. A little bit more accurately. Here is res 2 I'm creating now. And then I am plotting res and res 2 in the same plot. I've gotten rid of the fill, So it's just the outline of the bins. And then I've added E hat minus E and frequency, as you can see here. If you want to write mathematical E hat, that's how you do it. / hat. And then bracket your E. So now I am making a new figure. D over dx f of x. And measuring it over time. Now, if I want to make my plot, the line, I thought it was a little too skinny. There we go. Dots, can't see them now, so maybe I gotta do that. There we go. Here's where you put a bunch of plots in the same plot. I don't actually have values for any of the other ones. I just wanted to demonstrate that you can do this. This is how you would do that. Now, I love these. I absolutely love these vector maps. It's called a stream plot. And this is how I did it. And you get to return that. Now I did the same thing again. I just added more. And there we are. Some examples of how to use Python in the Jupyter Notebook to do some calculus, some linear algebra, and some plotting of any values that you need to plot or look at or investigate, any problems that you need to solve. Python is a very versatile language, and I'm glad that I know how to use it. That's for certain. It's awesome. I'm loving the programming. Thank you guys for watching. It's been awesome. If you like what you saw, like and subscribe. And I will be back with another video. That's for sure. See you then.